Tēnā koutou, tēnā koutou, tēnā tātou katoa. Kia ora koutou and good evening everyone and welcome to the festival. It's so great that you all turned out even though it was a horrible wet night. I was just saying to Michelle, I think this is the only place in New Zealand where that happens and people are so dedicated to coming to science events, so welcome. My name's Juliet Gerrard, and it's my absolute pleasure to be here tonight as a patron of the festival. I'm trying to see if I can get that changed to matron, but I haven't got there yet. And my job is just to introduce our very special guest, Dr. Michelle Thaller, who is here thanks to support from the US Embassy, who funded her trip. And as usual, we wish to thank the University of Otago, Dunedin City Council, and the Otago Community Trust, who are all generously supporting the festival once again. I was hoping to have met Michelle yesterday so I could give you lots of personal anecdotes about her, but sadly the weather put pay to that and cancelled my flight. So I'm delighted to instead much more formally welcome you tonight, Michelle, and we're absolutely thrilled that you're here at the festival in Dunedin. Michelle has a very long and detailed CV, and I'm not going to read it to you, but I'll give you a few highlights. So a recent edition of a NASA Exceptional Achievement Medal, which is NASA's highest honor, sits on the end of her CV. How cool is that? And this was awarded for a literally stellar 27-year career at NASA, building on an astrophysics degree from Harvard and fellowships at Caltech and the Jet Propulsion Laboratory. So as you're about to see, Michelle is not just a brilliant scientist, but she has a passion for communicating her science and has hosted hundreds of NASA events. She's worked with National Geographic, PBS, the BBC, and others to bring her insights to a wide audience. And she's also a podcaster and a TED speaker. So after you've enjoyed tonight's presentation, there's lots more of Michelle's amazing work to tap into online. Currently, Michelle is a professor at the University of Wisconsin and, intriguingly, and I need to ask her about this tomorrow, a part-time commercial fisher. We're absolutely thrilled that she's made time to visit us and talk about new discoveries and new connections. Nau mai, haere mai, piki mai. Welcome, Michelle.
Thank you. Thank you so much. All right, let me head up here. It is such an honor to be with you tonight, and I'm doubly honored that you braved the weather to come out and see us. So thank you so much. I'm already in love with Dunedin. I was looking at real estate online the other day. I mean, you have a real treasure here. You know, I had heard a little bit of Dunedin, but the density of incredible cultural assets you have here, the university, the museums, the galleries, restaurants, really nice little pubs, all of that. You know, I've been enjoying it, so it's an honor to be here with you tonight. And I want to share with you a little bit about things about science. Science is often presented in a way that seems very logical and dry, and to me, there's nothing more emotional or evocative than the beautiful things we see in the universe. And as well, a lot of people think about astronomy as being a study of things that are very far away. You know, we'll be talking about big distances tonight, things that are millions of times the size of the Earth or are light years away, and we'll talk about that. But astronomy is very, very much an intimate science. We are incredibly linked to it, and I hope you'll agree with me after tonight's lecture. So let me go ahead and get started. Make sure I can get my clicker there. I had the honor of being here for Mariki, and I always really enjoy the winter constellations coming back. The constellation Orion that you see up there in the right-hand side is probably my favorite constellation. And you know, it was wonderful for me to learn that the Maori believe that we came from the stars and we go back to the stars, and that's part of the observance of Mariki. So I found that very, very evocative. I actually did my dissertation on some of the stars in Orion's belt. Those are old friends of mine that I've spent hundreds of hours observing at telescopes. And they actually tell an incredible story about our connection, about life and death, and what it's like on a universal scale. So let me go to this picture of Orion. This is actually one of the first education products I made when I was a postdoctoral research fellow. That would have been probably back in like 1997, 98. And these are both actual images of the constellation Orion. My apologies, this is the Northern Hemisphere way. I should have just flipped the slide. I'll do that next time. But this is how Orion looks in the north. And this is an image of the night sky with obviously the blue bars showing you the shape of the constellation. And we're used to seeing space this way, as being dark with just sort of pinpricks of light being the distant stars. The other image you see of Orion is an actual image that was not generated by an artist or a computer. That was taken by one of the first satellites NASA had that could look at the universe in a different kind of light called infrared light. And infrared light is something that luckily people have become more and more commonly associated with, because it's what people usually think of as night vision. When you can image somebody in the dark, what you're really picking up is their heat. So we feel heat. I mean, you can sort of stick your arms out to a lovely warm campfire, and you can feel heat. That's actually infrared radiation. Infrared radiation is a type of light. It's the same kind of thing that our eyes see. It's made of a particle of light. It's called a photon. But infrared is too low of an energy for our eyes to detect. Our eyes only detect a tiny little bit of the available light. And this is one of the big challenges about being an astronomer, that the universe shines and shows you different things in different kinds of light. And infrared light picks up any type of heat that's coming from something in space. Things that are warm, but not necessarily glowing bright, like the surface of a star does in visible light. So here we see that there's a huge amount of dust and gas between the stars. Space is not very empty. This dust and gas is very, very thin. It is trillions upon trillions of times thinner than the air in this room. But it also fills in a huge volume. We will be talking about light years, and light years is a unit because astronomers, if they did everything in kilometers, would be basically writing zeros all day. So light, the speed of light, is 300,000 kilometers per second. And if you go at that speed for a year, you cover approximately 10 trillion kilometers. So when I talk about a light year, that's about 10 trillion kilometers. And when you have light years of this material, even though it's very thin, you can pick up the heat from it because there's so much of it out there. And also, the dust that you see here is actually quite cold compared to a human temperature. When I say something is warm, in astronomy, we basically mean it's above a few degrees above absolute zero. So the gas that you're seeing here may only be, 20, 30 degrees above absolute zero. But that's still enough to give us some heat. And it's amazing to think that the dark sky, if you were able to see heat light, Orion turns into this incredible, beautiful part of the sky. There's a star up here, Lambda Orionis, that is beginning to die, and it's shedding shells of gas. And we'll talk about that. The Orion Nebula right here, that's actually a place where thousands of new stars are being born. So let's take a look and see what that actually looks like closer. Now, infrared light is something that, that particular image was made by the IRAS satellite back in the 1980s. The most recent large infrared telescope launched was something called the James Webb Space Telescope, and that launched just a couple years ago in 2023. And you see here, one of the most wonderful things about working at Goddard Space Flight Center. So when I retired in October, I retired as the Assistant Director of Science at NASA's Goddard Space Flight Center. That's actually a base with 10,000 people. There are 10 NASA bases, and that one has 10,000 people. And we build robotic spacecraft. We have less to do with the astronauts and sending people into space, and more to do with all of NASA's science missions. So this is the mirror of our brand new space telescope. The mirror is about 7 meters across. So it's a very big telescope. It's actually divided into 18 segments and put together kind of like a honeycomb. And it is actually coated with gold, but the gold is very thin. It's just a plating. There's only about 5 golden rings worth of material in there. And this is actually being built in the largest and cleanest room that we know of in the world. It's actually large enough to fit 2 space shuttles inside. And it was designed for that when the space shuttle program was running. And you can see here that people are in what we call clean suits, or we like to call them bunny suits, because they remind us of little white bunnies kind of hopping around. I've been trying to get them to wear bunny ears for a while, but they haven't been able to do that. But anyway, this room is actually thousands of times cleaner than an operating room in a hospital. And that's to make sure that we don't get any impurities or little bits of skin cells on this incredibly complex, one-of-a-kind instrumentation. Now, the problem with such a big space telescope, and this is the largest and most complex space telescope launched, is that we don't have a rocket that's big enough to launch the whole thing put together. It's too big of a telescope. And so the telescope, the reason we had it in segments, each segment can focus itself individually and form a perfect mirror shape. We have to fold it up to actually get it on top of the largest lift rocket in the world, which is the Europeans' Ariane 5 rocket. So the telescope had to be designed to fold up like origami. And the thing that was incredibly nerve-wracking, and a lot of the gray hairs you see came from, is that there were over 340 commands that we had to actually deploy this telescope once it was in space. It was going way far out. It's actually going about 1.6 million kilometers away from Earth, farther than the moon. So nobody can fix it. And the thing that I think a lot of people don't really understand is there are no backups, because a backup would mean more mass. And when you're launching on a rocket, every milligram counts. I mean, if there was a little pulley to kind of deploy the mirrors and little engines that had to do that, if you had a backup one, that would mean you couldn't have an instrument on the telescope, or a camera would have to be left off. So mass is incredibly important. So nothing had a backup. 340 single-point failures, and it would just be a piece of floating space junk. So this was very, very difficult for a lot of us. But I want you to come along with me in the next slide. This was getting ready to launch, up to our launch. Everything you see is real movie cameras taken of the launch and the deployment of the telescope. The Europeans' launch site is in French Guiana. It's a French territory in the northern part of South America. You always want to launch close to the equator, because the Earth rotates quite fast. You know, the Earth is rotating at, say, approximately 90,000 kilometers an hour at the equator. At the pole, once every 24 hours, you make much smaller circles. So if you launch near the equator, the Earth is already moving fast enough to kick you part of the way out. And so here's the telescope. In this case, instead of bunnies, I was thinking they're marshmallow bunnies, they're yellow. And there you see the clean tent on the very top, putting our telescope on there. The Ariane 5 is as large as a 10-story building. It's a huge thing. Everything NASA does in terms of major projects is a collaboration with other nations. This was a collaboration with the European Space Agency, a big collaboration with Canada. We collaborate a lot with New Zealand on Earth science. And here we have that terrible morning, it's thunderstormy, but the launch goes off anyway.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
This is a real picture from the top of the rocket and camera. So there's that telescope. And now you're looking at sort of the bottom side of it as it heads off into space. And we were so relieved to see the very first deployment, which was a solar panel. Now we knew that it was able to generate its own electricity. So there goes our baby. We started working on it in 1995.
The James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery.
And that's what it is. I mean, this is something for pure discovery. And it actually stands on the shoulders of giants. The space telescopes that have come before have all informed us how to make a better one, a bigger one, a more sensitive one. And this is a picture, a famous picture actually from the Hubble Space Telescope. So the Hubble Space Telescope has been around my entire career as an astronomer. I think we're getting fairly close now to its 40th anniversary, which is pretty amazing. And if you've seen this image before, it's commonly called the pillars of creation. And I think that's actually a very apt name for this. You're looking at a cloud in space. But unlike here on Earth, it's not made of air and water vapor. Clouds in space are mainly made of hydrogen gas. But everything that you see that's kind of dark and schmutzy and dusty looking is in fact dust. And it's dust very similar to the dust you find in this room. There's a lot of carbon stuff in it, graphites, things like pencil markings, silicates, all sorts of heavier elements. Now, this is an amazing story as to where this dust comes from, but let me talk a bit about the scale of this particular cloud. So we mentioned light years, a light year being about 10 trillion kilometers. And this particular column of gas here, this big tower of gas and dust that you see, is approximately 5 light years long. And one of the reasons I love coming to the south here is that you're able to see the nearest star to us, Alpha Centauri, in the night sky. In the north, you can't see it. It's one of the pointer stars to the Southern Cross. And the nearest star to us is a little over 4 light years away. So that means that this column would fill the space between us and the nearest star. And as I mentioned, it's very diffuse dust and gas, but you have light years of it. You have tens of trillions of kilometers. And to build a star, all you need is gas, dust, and gravity. Simply allowing gravity to start bringing together denser parts of the cloud. Some parts are denser than others. That means they attract a little more matter around them, gravitationally, just gravity. From any direction, gravity is bringing stuff in. But now you have light years of material to draw on as gravity brings things more and more. As the gravity draws the gas together, when you crush gas together, it actually heats up just naturally. Until finally, in the cores of these clouds, the temperatures get to tens of millions of degrees. And that's enough to start a nuclear fusion reaction. That powers the star. That's what powers our sun. So I want to show you, this is a beautiful picture. This is what Hubble took. Here's what the James Webb Space Telescope took of the same cloud. And you see how there's always an uncovering. There's always a new opening of eyes. The James Webb Space Telescope is literally a set of eyes the universe has never seen through before. It's a new sight. And you'll notice that we were missing some stars. And some of the stars that you see are actually so far away, they're actually not associated with the cloud. Like over here, these are stars that are probably way past the cloud in our galaxy. But the dust from the cloud was actually absorbing the light as it came towards us. So some of these stars are very far away. Some of the stars probably are associated with the star-forming cloud. But the real action is happening at the tips of the pillars. These are denser areas of the cloud, and they're beginning to heat up inside. And so we have many different colors of infrared that we can look at. So here's another one that I thought kind of brings out the beautiful structure of the cloud. This is an image your eyes could not see. So this is all in infrared light. This is all a real detection. It's a real image. Everything you see here was an actual particle of light hitting our detector. But we're shining now in a color that you don't so much see as feel. This is what happens when you image the heat from that cloud. And as you see, right at the tips of those columns, there are sort of reddish areas, especially here. Here I think there are some new stars that have just turned on that are beginning to erode away the cloud. But I always just want to take a little moment to appreciate the beauty of this. And going into sort of the middle one a little bit closer, you can see that inside, deep inside here, there are little warm areas, little knots of activity where the stars are actually forming today. So, a beautiful new image from the James Webb Space Telescope. When you look inside these clouds a little deeper, and this is a different cloud, but this would be totally covered up with dust. You wouldn't be able to see it in visible light. This is actually the moment a star turns on. Now stars do everything in big amounts of time. So the instant a star turns on could last tens of thousands or hundreds of thousands of years. But what we see here is a dark part of the dust cloud. It's actually covering up a newborn star inside. The dust is so thick you can't see through it. But coming out are these huge jets that are trillions of kilometers long. And they are the herald of a new star. They're birth pangs. when a star first begins its nuclear reactions, they're sort of unstable, and material gets thrown off, and it gets directed along the poles of the star, the magnetic poles. And so what you're seeing here is the moment, which takes some time, but you're seeing the birth of a new star in a new solar system. And that remaining cloud of dust that's kind of around the young star becomes pretty important. Here's another picture of a young star. Again, this is an image from the James Webb Space Telescope, deep inside a cloud that's forming stars. And now it's gotten a little more organized. The young star is in here. It's still covered up by a rotating disk of dust that's just left over from the cloud. As stuff was coming in under the force of gravity, a little bit of the dust of that cloud began to spin around in a disk around the young star. And you can see the jets. There's a new jet there. There's one down here that's actually still a bit covered up in the dust cloud. And all this wonderful gas structure being lit up by the new star. This is a rotating disk seen edge on. And this disk is about 300 times the distance between the Earth and the Sun. And you may think, that there's something pretty important that's going to go on in there. Just the leftovers of forming a star, a little bit of stuff that gets left over orbiting around, will eventually become a solar system. And then this is one of my only artist conceptions. So we don't have a very good high-resolution picture of a young solar system. But inside that dust, this is what is happening. Gravity is clumping together that dust, and over time, you have the planets forming, you've got the new star in the middle, the planets are orbiting around in this wonderful disk of material, gaining mass. You also have lots of little leftover things. You see here, there's things that look kind of like comets, little icy particles. We're going to come back to those at the end of the talk. So a lot of stuff gets built into planets, but there's always a little bit of leftover stuff, and that actually becomes very important. This is a picture from a ground-based telescope of a young cluster of stars that is turned on. And what they're doing now is that the heat and winds of high-energy particles from these stars is blowing away the cloud they were born out of. We no longer know where our birth cloud was. We no longer know which stars in the galaxy formed with us. We fly around the galaxy at approximately, say about 800,000 kilometers an hour, going around our galaxy. That actually takes us about 250 million years to go once around the galaxy. But in the history of the Earth, we've been around about 20 times around the entire Milky Way as we orbit around with the sun. And as that's happened, our brother and sister stars have moved away from us, and we don't know which ones they are. For those of you that like astronomy, this is called the Rosette Nebula. And you can see the beautiful dust that's in this cloud. You can see the young stars here in blue, and they're blowing a bubble in the cloud. And there are probably other stars hidden in here that are still forming. So a beautiful picture of what happens when stars turn on and begin their lives. So this next one I'll talk a bit through. I could watch this movie. All of this, by the way, is free and available from the NASA website. We have an observatory at NASA that takes incredible high-resolution images of the sun. And we take a high-resolution image every 12 seconds. And we've been doing this now for about 15 years. This was made about 10 years ago. The telescope is actually particularly sensitive to very hot gas, where there's activity on the sun. Solar flares, prominences that are actually lofting trillions of tons of material. The sun is so big, you could fit 1 million Earths inside it. Across the diameter of the sun, you could fit about 110 Earths. So as we watch these movies unfold, think about the scale that you're seeing. It's incredible. These are real movies taken with real data, but they were sped up in time because these wonderful explosions and the sun releasing material. There's Venus, by the way, photobombing. So all of these are sped up because they took hours. The sun is so huge. These interactions took hours to unfold. But this is all real data. Look at that. The sun sometimes lofts up, as I mentioned, trillions of tons of hot hydrogen, hot material into space. And this, as data has come in from this telescope, of course we're studying it as scientists, but we also just have to watch it and say, wow. something that it fills me with awe every single time. I just can't look at this movie and not respond to it. It is so beautiful. This is real. That's what our star looks like close up. Every one of those giant streamers of hot gas you could fit the Earth under, I would think. That's a solar flare. It's a burst of high energy radiation, X-ray light even. And what's left behind is a roiling cauldron of hot gas, some sunspots. Yeah, that's shooting off ones. Yeah. Just beautiful. So we talked about the formation of a star, but I think one thing to really kind of emphasize and nail down, a star, the interior of a star, the very core of a star, is the only place we know of in the universe where there's enough density and heat to actually cause a natural nuclear fusion reaction. And of course, this is the same thing that powers fusion reactors. New Zealand is actually a leader in fusion energy. And it's also the thing that powers things like hydrogen bombs. You just take small atoms, you ram them together with such force they stick. And when that happens, huge amounts of energy are released. So the simplest atom, the simplest, smallest atom is hydrogen. You ram two of these together inside the core of a star, you get helium, the next largest atom. Helium can actually be made then if you ram helium atoms together into things like carbon and oxygen and nitrogen and phosphorus and sulfur and calcium. This is the only way the universe has to actually make those atoms. You may have noticed that when the James Webb Space Telescope launch footage was going off, they said, here goes James Webb on a journey to the beginning of time. That is literally true. The James Webb Space Telescope is so powerful it can see things very far away. And as fast as light travels, it takes time. So the sun takes light about 8 minutes to get from us to the sun. So when you see the sun in the sky, you're looking at it as it was 8 minutes ago. The nearest star to us, Alpha Centauri, you see as it was about 4 years ago. The nearest large galaxy to us, Andromeda, is 2 million light years away. So when you see Andromeda in the night sky with a pair of binoculars, you're looking at it right now. You're looking at that from a time before modern humans, a time when things like Lucy and Australopithecus were around. We can now see so far out into the universe that we're looking back more than 10 billion years. In fact, the farthest we see, not with this telescope in particular, but we have another one at NASA that can see so far back to a time, it's about 400,000 years after the Big Bang. The universe was only hot hydrogen. It was about the temperature of the surface of the sun. Think about that. The whole universe full of hydrogen gas, so hot it's glowing like the sun. We can look so far back that we see to that time. It's not a theory that there weren't any elements that make us up at that time. We can take a picture of it. Stars are responsible for building every other atom besides hydrogen and helium. There's no other way to get what makes us up. The way these materials then come from a star to us is an incredible story. What we have here is a picture of a star that instead of being born is now dying. It's run out of nuclear fuel. There's a limited amount of nuclear fuel in the core of a star. And eventually that gets used up, the nuclear reactions begin to peter out, and the star dies. And for stars about the same temperature and size of the mass of the sun, they gently unravel back into space. And that's what's happening here. There's a star down here, again, covered up by sort of a disk of dust orbiting around. Deep in here, there's a star that used to be like the sun, but now it's unraveling its material across light years. Every star dies a little bit differently. It's a beautiful thing. This is another nebula, another cloud caused by a star gently unraveling itself into space. This is a picture. Okay, this is an image from space. This is not a painting. It is so beautiful how these things unravel into space, in this case fairly gently. If you're a little more massive than the sun, the death is a bit more violent, And you get something called a supernova explosion. This is a famous supernova explosion called the Crab Nebula in the constellation Taurus. This star died about 1,000 years ago. It was bright enough in the sky, it was recorded by people all over the world in many different cultures. And the explosion in some ways is really still going on. You're looking at a cloud in space that is about 10 light years end to end. And so one star now is distributing its material over 10 light years, and the outside shock that's coming out from this explosion is still going about 3 million kilometers an hour. So this explosion 1,000 years ago is still unraveling itself into space. This is one called the Vela supernova remnant. Vela was a long ago star that exploded, and now these tendrils of gas and dust, enriched with all of the elements that star made, are now spread over more than 50 light years. A single star dies and brings all of these riches to the galaxy. So here's a picture of a galaxy from the Hubble Space Telescope. And a galaxy is a family of hundreds of billions of stars. We live in the Milky Way galaxy. The thing that's amazing to think about is that all of the dark material, so every little dot you see here is a star, but I've always thought that galaxy is a really easy word to say. But people have, I have the same kind of brain you do. I have no more ability to comprehend what a million means or a billion means. I think human brains go up to 7, and then we're kind of, if we talked about how the sun is so huge you could fit 1 million Earths inside it. So if you put 1 million Earths inside the sun, and then now let's make the sun the scale of the dot of an I on a page of text. So if the sun were at that scale, 1 million Earths inside the dot of an I, a typical spiral galaxy would be a little larger than the Earth. It's a monster. It's vast. And all of this dark material is material thrown off from dying stars. Everything that you see here is enriched with that carbon and that silica and that iron and the phosphorus. You know, the iron that makes your blood red actually is only formed in a supernova explosion. So we move around the galaxy, as I mentioned. We're moving around on the order of about 700,000–800,000 kilometers an hour. This is a picture of a spiral galaxy from the James Webb Space Telescope. And you now see all of the warm dust, all of that thrown out from dead stars, dying stars. We move around that. We've been over 20 times around the galaxy, picking up material from the entire galaxy. We estimate about 100 tons a day. There is nothing in the universe that makes what you are made of. The hydrogen was made in the Big Bang. There's not a whole lot of helium around. Some of that was made in the Big Bang as well. But everything else had to be picked up from space as we go around the galaxy. You're not made of just one star that died. You're not made of 1 million stars that died. In our bodies right now, in every single one of us, are the remnants of billions of stars over billions of years. Each and every one of you is a galaxy made conscious for a moment. And it's one of the reasons I think people should know this. We are all cosmic treasures. The universe has one chance to see through your eyes. There will never be another person like you. This is your one chance to be the galaxy made awake. Now, I don't like a lot of charts, but I figured I'd put one in the periodic table. For those of you that study chemistry and for those of you that are learning it, these are all of the different kinds of atoms that are available. Each different element on the periodic table is just a different kind of element. It had to be put together inside a star. And now what we can do is we can actually trace which of our chemicals came from what kinds of stars. Some of our elements, like I mentioned, hydrogen came from the Big Bang. That's in water, H2O. You need 2 atoms of hydrogen in every bit of water. Some are from dying low-mass stars like the sun. Some are from dying high-mass stars. I wish I had more time to tell you about this, but the ones where you see 2 bright objects spiraling together, the only time we've observed the universe making these particular chemicals is when 2 dead stars called neutron stars spiral together and collide. And they produce an explosion so violent, we don't have the physics to describe it yet. It actually defies our current laws of physics, how bright and powerful these explosions are. We find them because these explosions are so intense, they shake the fabric of space and time itself. I'm not exaggerating. We find them by looking for vibrations in space and time. That's in your body. Interestingly enough, iodine. The only time you've ever seen iodine. So next time you have salt, think about that. Gold, silver. I don't know whether people take Pepto-Bismol, but bismuth is only seen in these titanic explosions we don't even have the physics for, and that's now in like stomach remedies. I mean, it's really kind of amazing to think that now we know where all this comes from. So I want to tell you about another mission that just ended recently. Both the Webb telescope and this next mission were things I worked on a lot, and that's why I retired, was things had sort of had wrapped up. But is there a way that we can go a little further, instead of just knowing where our atoms come from? What about our molecules, our organics? What about our DNA? Is there any possibility that some of that actually comes originally from space itself? To do that, we would need to take a sample of what our dust cloud was like. We know what the disk of dust orbiting the young sun was like before there was life, before things collected into planets. What was our chemistry like? Let me put that a little bit more vividly. What were we like before life began? So this is an artist's conception of small bodies coming together to make larger and larger planets. But as I mentioned, there's always some stuff kind of left over that did not get incorporated into bigger planets. And it turns out that the University of Otago is one of the best places in the world to study that. You guys should be very, very proud of that. So this is Marshall. He's at the university, and he's a professor in geology. And he has come up with a wonderful system. The project is called Fireball. And you can buy a cheap camera to put on your roof. And the camera will scan the sky at night for shooting stars. Ones that get particularly bright called fireballs. A shooting star, a meteor, is when usually just a little bit of dust from space comes into our atmosphere. It's going so fast, it burns up. A fireball is when there's probably a rock big enough left at the end of the descent through the atmosphere to collect. We call that a meteorite. So it's a meteor when it goes through the atmosphere, and if anything is left over on the ground, it's called a meteorite. So this will actually track where fireballs come through, and you can actually use this to find meteorites. So this was from the University of Otago's press release back in 2024. They found the 10th meteorite identified in New Zealand. What had happened was all these people had cameras. These are just citizens. They're not professors. They're not academics. They're just people that volunteered to have a camera on their roof. A fireball was seen, and because people were seeing that from all different directions, all around the town and all around New Zealand, they were actually able to triangulate and pinpoint where the rock should have landed. And amazingly, they found the meteorite within 30 minutes of searching for it. So absolutely incredible. Okay, now, why are we interested about these little rocks from space? These small bodies, these meteorites, they're actually from a time before the planets were formed, many of them. They're actually little things that got left over that weren't made into bigger planets. They weren't modified by heat melting the core of our planet, or water, or air. All of that, they're basically up there in deep freeze for billions of years. And samples of meteorites are incredibly important pieces of the story of life. How did our molecules get to the surface of Earth, and what was in them? These are astrobiologists. That's Deborah and her two postdocs at Goddard Space Flight Center. And they're actually holding up, in this case, tiny little samples of the moon. These were actually little samples brought back from the Apollo astronauts. And the moon as well has not been modified. The surface is billions of years old. So there's a lot of clues up on the lunar surface too about what was around when our planets were forming. We also send our wonderful planetary scientists to pretty remote locations looking for meteorites. And here you see some very excited scientists from Goddard. They've identified a meteorite in Antarctica. And Antarctica turns out to be a wonderful place to find meteorites because the local rock is about 1 kilometer under the ice. And not only that, the glaciers on Antarctica move sort of towards a trans-Antarctic mountain range, and they drop their rocks there. And not every rock is a meteorite, but there's more than you'd think. So we send them out on snowcat trains, and we actually have them look around the ice shield for meteorites. So there they found one. And then we bring it back to our laboratory at Goddard. And so starting about 15 years ago, this wonderful group of astrobiologists, these are all incredible people, they're my heroes and my friends, they began to identify amino acids, the building blocks of our proteins, were already present in meteorites. And I had to just kind of show you this. So this was for the Science Journal. They all look very dramatic. We have dramatic lighting in a laboratory. That would never happen. And that's actually what they look like. So when I saw this, so Jason is a very shy, kind person. And the fact they have him looking like really dramatic, I mean, we love that when they do that to us. It's just so embarrassing. All right, well, how about a step further? Okay, meteorites are a sample of that disk. But can we get a sample before it falls flaming through the Earth's atmosphere and lands on the ground and gets contaminated by Earth bacteria or by soaking in water? Can we get a pristine sample of what our disk was like before life? To do that, let's go to one of the small bodies that's been unchanged for billions of years, a small asteroid. And this is an artist's conception of a spacecraft that we sent out to an asteroid. The mission's called OSIRIS-REx. It's one of the worst acronyms NASA has. The Origin Spectral Interpretation Resource Identification Security Regolith Explorer. Thank you, yeah. OSIRIS-REx is about the size of a small car. And the idea was to actually send it to an asteroid and then literally just have it vacuum up some pristine material before it ever even gets to Earth. And I want you to pay close attention to the fact that the asteroid that we have, this was before the mission. We drew an asteroid that looks nice and smooth, and it's very easy just to tootle around and just kind of vacuum up some nice particles. So that's what we were expecting. We chose an asteroid called Bennu that in its orbit actually comes near to Earth. So when we actually went out to take the sample, Bennu was about 300 million kilometers away. But then the asteroid itself moved close to Earth in its orbit, and we were able to actually take a sample and shoot it back to Earth. So this was the asteroid Bennu. It's about 1/2 kilometer across. It's relatively small. And this was one of the first pictures we took of it. The asteroid spins around. And notice it's a little bit wider at its equator. It spins around once every 4 hours. It looks like there may have been some collisions, some craters. Everything was going okay. Then we started looking for a good site to go vacuum up some material. And the closer we got, we realized we were in pretty big trouble. The whole asteroid was full of very large rocks on the surface. To give you an idea, this big boulder up here is 20 meters high. And our canister was designed to pick up nothing bigger than like an aspirin. So we'd gone 300 kilometers, and we were scared. I mean, we were really wondering if there was going to be anywhere to pick up material. We scanned the entire asteroid, and we found only 4 sites that had sort of a little bit of an impact crater, and there was a bowl of dusty stuff. But the spacecraft was never designed to be autonomous. I mean, we thought we could just send it down, and then it would just come back up again. The light travel time for commands was 15 minutes each way. And the boulders now were so big that the spacecraft would have to learn how to navigate down between the boulders. We taught it at the asteroid. We updated its software. We taught it how to be self-aware of the barriers around it, where the boulders were, and to be able to say, I'm going down, but I'm going to hit something, so I'm going to call it off. So we actually taught it to be autonomous when it was already at the asteroid. And we basically crossed our fingers. This is the artist's conception of what's happening. It had to maneuver down into an area about the size of 2 parking spaces for a car. It had not been designed to do that. And so, I mean, these are some of the things that we had to do on the fly. And this is an actual movie of the little vacuum cleaner coming down to the surface, where hopefully the particles are going to be pretty small. We actually broke through a crust. And it turned out that it was almost kind of like a ball pit. There were kind of little jumbled together rocks, bits of everything. And but there we have our sample, and we put the sample in a little canister. Oops, let me do that so it closes the canister, right? Never mind. Then the canister parachuted back to Earth. We sent it back to Earth. It landed in Utah, and there's the real deal. There is a little sample of an asteroid, a little sample of our chemistry before life formed, in a container, kind of dark and burnt up from the re-entry of the atmosphere. So I'm going to end on a short video that talks about what we found in that asteroid. Here's opening up the canister, and as you can see, there's a wonderful deposit of this more precious than gold preservation of our selves, of our life, billions of years ago.
The origin of life is one of the deepest mysteries in science, but the clues to solving it have been buried by plate tectonics, the water cycle, and even life itself. For answers, scientists are looking beyond Earth to primitive asteroids like Bennu, the target of NASA's daring OSIRIS-REx sample return mission. Now, material from Bennu is revealing a lost world from the dawn of the solar system, with the right conditions to foster the building blocks of life. When scientists examined the Bennu samples, they discovered evidence of a wet and salty past. Among the dark rocks were bright veins of salts that form on Earth when brines evaporate from alkaline lakes. Searles Lake, California is home to a mineral called trona, which is mined as a source of baking soda. Scientists found microcrystals of trona and other evaporite minerals within the Bennu samples, indicating that they once held pockets of sodium-rich water. Such brines are ideal for cooking up organic molecules, carbon-based compounds that are the stuff of life. Bennu is a carbon-rich asteroid, and its samples are chock full of organics, including amino acids and nucleobases. Amino acids can be bonded together in long chains to build proteins, which give cells their structure and function. Life is constructed from a set of 20 amino acids, 14 of which were identified within the Bennu samples. Nucleobases are the genetic components of DNA and RNA. All 5 nucleobases were discovered in the Bennu samples, a first for extraterrestrial material collected by a spacecraft. In addition to organic molecules, scientists found that the Bennu samples are surprisingly rich in ammonia. On Earth, ammonia is a common agricultural fertilizer. It readily evaporates at room temperature, but is more stable in cold environments, like those found in the outer solar system. Bennu is too close to the Sun to retain pure ammonia, so its samples must have formed during a more distant, frigid past. Salts, organics, ammonia. Thanks to OSIRIS-REx, we can now piece together these clues to tell a likely origin story for asteroid Bennu. 4.5 billion years ago, in the nascent solar system's outer reaches, a world of rock, metal, and ice took shape. Radioactive decay heated its interior, melting some of the ice. Pockets of mineral-rich water reacted with formaldehyde and ammonia to produce organics. As the water dried up, the dissolved minerals crystallized, leaving bright veins within the rocks. The world migrated closer to the Sun until it was shattered in a collision and destroyed. Bennu accreted from the rubble and drifted further inward, eventually settling into a near-Earth orbit where it could be reached by OSIRIS-REx. Our planet was bombarded by asteroids like Bennu early in its history, suggesting that many of the same organic molecules were present on Earth before the dawn of life.
It's an amazing thing to think, we go out to this asteroid, we travel 300 million kilometers, and inside that asteroid are all of our nucleobases, every letter of our DNA and RNA. There's water dissolved in the mineral. It turns out the water in our bodies and the water in the oceans is an exact chemical match to that water. The Earth is a rock planet, a rock and a core of metal. There's just a tiny little scrum of water on the outside that we call our oceans. We think that pretty much all of that most likely came from asteroids. And it's no coincidence that our DNA is built out of things that are raining down from us from the sky. It's the study of us. As I mentioned, astronomy isn't the study of something distant. When you look at the night sky, you pick any star in the night sky, there is an atom of iron in the blood in your heart right now, and there is an atom of iron in the atmosphere of that star that were formed in the same explosion, the same supernova of a star that died billions of years ago. We are their brothers and sisters. We are related to them. You have molecules, you have atoms from the entire galaxy in your body right now. So these are things that connect us to a larger universe. I mean, I find them very emotionally evocative. I love the fact that in the wisdom of the Maori, we came from the stars and we will go back to the stars, and so we will. When the sun dies in billions of years, we will become that dust spread out over the galaxy to form new planets and new life. And what old worlds and what other life could your atoms have been part of billions of years ago? This is what astronomy is about, the knowledge of who you are. And each of you has shared a little bit of your time and your existence with me tonight, and I'm honored by that. So thank you so much for coming, and it's a pleasure to share a little bit of my world with you. Thank you. I'm here to take some questions. I should mention, this is a brand new image. I don't know if you heard on the news, but there is a new ground-based telescope called the Vera Rubin telescope. It's the biggest camera ever created to look at the sky. It's a 3 billion pixel camera. And this particular image that was just released is a composite image of over 2 trillion pixels. And this camera is going to image the entire night sky every 3 days. I mean, you just think about the data that we're going to have. It's just unbelievable. So I think people are coming around with a microphone. If you have something else to do, please, we're all friends here. You can get up, you can leave, you can do whatever you like. But I'm happy to stay and take questions for as long as people would not want to. So, and I hit a cup of water here. So, always know where your water is and your towel is.
How do you suck, like, the spacecraft thing? How do you suck the rock up in a vacuum?
Yeah, how do we actually create the suction?
Yeah, in a vacuum.
Really interesting. We actually use the vacuum of space itself. So, space itself has no air. And so when we opened the canister, there was sort of a difference in pressure that we used to actually drive the vacuum. So it was sort of a case of exposing part of it to space and then sucking up what space itself was kind of moving. So I mean, we actually use the vacuum of space as a way to create the pressure for the vacuum cleaner. Yeah, and I mean, so that's exactly the kind of thing that you do when you become an engineer at NASA, is, how do you make something that will work when there's no gravity, there's no air. In the case of Bennu, it's too small to really have any gravity, and all of that. How do you design something that will vacuum up a sample from space? And it's been a huge privilege, for me. I mean, I'm a physicist. I do more of the actual physics of what's going on. But more people at NASA are engineers who build these things and design these spacecraft. And as you can see, software engineers are really important. People are sort of like, well, you're not a real engineer if you're a software engineer. I mean, we wouldn't have been able to do this mission unless we could reprogram the whole spaceship all the way from 300 million kilometers away. Yeah.
The stars that you can see there in the nebula, are they behind the nebula shining through, or are they in front of the nebula?
In this image here, do you mean this image or one of the ones of the Pillars of Creation? Yeah, okay. The Pillars of Creation one, the majority of stars you see in that image are actually behind the nebula. So the nebula is this diffuse cloud of gas and dust, and the stars could be quite far away. They could be dozens of light years away, maybe even hundreds of light years away behind the nebula. But even so, their light had been stopped by the dust that the nebula has in it. And so when you take the infrared picture and you're able to image the heat can actually get through the dust. And so you can image stars that are very far away. Some of those stars were associated with the nebula and were new stars there, but the vast majority were stars that were behind it. Yeah, absolutely.
Kia ora. Thank you very much for your talk. It's been fascinating. Just wondering, how does the gravity that attracts the dust first start? Because do you need the density first, or what causes gravity?
The amazing thing is that anything with mass has gravity. And it's something, I mean, right now we are all overwhelmed by the Earth's gravitational field. Everything we drop goes straight down, all of that. I remember one of the fun problems I did when I was a physics student is if you take 2 gaming dice and you put them in space where there's no gravity and you put them on the order of maybe 5 centimeters apart, the calculation we had to do is just the mass of the 2 dice. How long does it take them to come together? And it's surprisingly short. It was something on the matter of an hour or so. That when things are floating without the influence of Earth's gravity, you actually see this effect of even little small bodies get attracted to each other. And so but what you first need is you need an area of the cloud to become a little bit more dense. And it's a huge field of study as to what does that. Why does a cloud decide to start collapsing? A lot of times there's a nearby dying star, a supernova, and it explodes, and that actually kind of smacks the cloud, and that creates denser areas in the cloud. Sometimes we see stars forming, and the birth pangs, all of the outflow of particles from the newborn star, again, creates kind of a shock wave in the cloud and creates another generation of stars. But then there's the question about how did it start in the beginning, right? I mean, before there were any stars at all. Did it have something to do just with the rotation of our galaxy, or the way the dust clouds that formed the galaxy, or not the dust clouds, the gas clouds that formed the galaxy came together? So nowadays we see star formation being triggered by other events. And one of the things that's a little bit sad is the rate of star formation is very definitely going down in the universe. When you look at galaxies far away and you're looking billions of years back in time, there were far more stars being born. And it's kind of stars, the way that we think of stars is that they're kind of a remnant from the Big Bang. You still have hydrogen gas, everything is still kind of close enough together, gravity can bring things together. There will be an end to stars, we believe. There's only a certain amount of hydrogen, and most of that hydrogen is just between the stars. It's not even in a galaxy. And so there will become a time when stars just don't form anymore in trillions and trillions of years. So, I mean, I wonder if there are people then, I think that or whatever sort of intelligent life, will they think about this being a time of like the Garden of Eden, where free energy came pouring out of the sky, and you could just snuggle up to a warm burning ball of hydrogen and have all of this this warmth. That will end eventually, we believe. Yeah. Yes.
I have less of a science question, more of a practical naming question.
Absolutely.
So like NASA and JAXA and the ESA and all the different space agencies, who gets to name new nebula or stars or discoveries, and then is it kind of named similarly across, or does everyone kind of name different?
Yes, okay, so naming conventions, absolutely. So there's something called the International Astronomical Union, and that's a professional organization that astrophysicists all over the world belong to, and they have conferences and they have meetings. Famously, one of my favorite solar system bodies is Pluto, and I don't care whether you call it a planet or not. It's a fascinating world. But it was there that they voted to declare it a dwarf planet, which I think is kind of misleading. But the International Astronomical Union names all of the stars and nebulas, and I mean most like planets around other stars. I mean, we now know of so many of them. Those basically have like phone book numbers and catalog numbers. So there's nobody except the International Astronomical Union that names stars. So if anybody has done that, buy a star and all that, it's actually not real. They'll name a star after you. I'm sorry, it's not true. But the other naming conventions is that if you discover a comet, then the comet is named after you. So comets are always named after the discoverer of the comet, and if it's more than one person, it just becomes a hyphenated name. And then if you discover an asteroid, if you discover a little, and then those are actually commonly found. We find little asteroids all the time. You get to name it. So there's all the Beatles are up there. Frank Zappa is up there. People name them after their dogs. I mean, you get to name the asteroid yourself. So asteroids you name, comets are named after you. Stars and nebulas and all of this is named by the International Astronomical Union. The NASA missions, NASA does pick the names for those, and they're controversial because, like James Webb, for example, was a politician. He was the head of NASA during the Apollo program, but he wasn't a scientist, and that was partially done to save the mission from being canceled because James Webb was a Republican, and sometimes the Republicans want to cut science, so we try to name things after them. But honestly, you don't want to cut your own, But anyway, the Vera Rubin telescope that I mentioned here. I mean, Vera Rubin was a real hero of mine. I got a chance to meet her maybe half a dozen times. She's passed now, and she was one of the discoverers of dark matter. And she was doing that back in the 1960s, where they often wouldn't let her use telescopes in observatories because they told her there were no women's restrooms. And it's amazing to think how much things have changed. I did most of my doctoral research in Australia, and We were all okay with using the restrooms together. We also had Charlie, the resident Huntsman spider, that I did meet in the bathroom. And nobody told me how big Huntsman spiders were. I know they're harmless. We never did anything to hurt Charlie, but someone should have told me. Monster, yeah. Oh yes, question.
Yeah, sorry if this might be a really stupid question, but
There's no such thing as anything. Give it. I love
you
it.
just wait. You just wait. I've always wondered this, and I've never really got an answer. But at the Big Bang and the expansion of the universe, right at the start, the expansion was, I think, faster than the speed of light. So how's that possible when the speed of light's the speed limit? How's it possible something is moving faster then?
Absolutely.
Or
yeah.
did the rules of physics just not work back then because it was too early?
So I mean, you've just answered. I mean, you see this as a stupid question. I mean, you just ask a question that that was like a Nobel Prize worthy question, right? So one of the things you have to separate is the things that we can observe and measure now, and the things that are still conjectural, the things that we've made our best guess given our understanding of physics. And what you're talking about is something called the inflationary universe theory. And this was started back in the 1970s by a man named Alan Guth. And he basically combined some of the ideas of astrophysics and particle physics to try to figure out what the very first moments of the Big Bang might have been like. Now, it's worth mentioning we have 0 observations of that. I mean, we're talking about a time that was a trillionth of a second before the Big Bang, or sorry, after the Big Bang. And we can observe what the universe was like as far as data about 400,000 years after the Big Bang. So this is conjecture. But it makes a lot of sense. It actually matches what you see quite well. And the idea is that there was this time when all the forces of nature were kind of one single force together. And as the universe cooled, the forces themselves kind of fractured into the different forces we know, and that gave space a kick. And this is actually, it's an amazing question because it brings about one of the biggest misconceptions about the Big Bang. I know I'm going to kick that over. It's water though, so. The Big Bang is not an explosion away from an empty center and galaxies flying off into empty space. That's often portrayed that way, like on television and in movies. And it's just not the way it worked at all. We don't think the galaxies are actually moving through space. And then this is the faster than light thing. So it seems like space itself, empty space, has some kind of pressure that makes it expand. And so when I was teaching this in college, I would take a piece of wood and a piece of elastic, and I would nail down 2 nails and say, those nails are the galaxies. They're sitting in space and time. Space and time is the elastic between them. And then I would take the elastic and pull it. And I would say, the galaxies aren't really moving anywhere. Space itself between the galaxies somehow has this pressure to expand. And I mean, we don't understand why yet. We don't understand what set off the Big Bang yet. So the idea that you can see, and we do, we observe galaxies that are apparently moving faster than the speed of light away from us. And the explanation is that the galaxies aren't actually moving faster than the speed of light. Instead, you're looking through a lot of space that's all expanding. The farther you look through space, the more you're looking through expanding elastic. And so the farther away you see something, the faster it seems to be going away from us. Because you're looking at space, a lot of space expands a lot. And so it's not really motion. That's our current idea. I will say that we are very much aware that the telescope was only invented about 400 years ago. And in another 400 years, will they just laugh at that, right? It's part of being a scientist. It's something that I love about being a scientist, is that our best models change sometimes. And even the expansion of the universe is only about 100 years old. Hubble observed it in the 1920s, about 100 years ago. So, and then 2 of my friends from college, and boy, this will give you an inferiority complex, 2 of my friends got the Nobel Prize in 2011. And they got it they were trying to measure how much the Big Bang was slowing down over time. And you probably heard, nobody expected this, but the measurement 3 different independent groups got, very good scientists, is that the universe is going faster now than when it first started. That's crazy. No one expected that. And the next big space telescope that we're launching, the Nancy Grace Roman telescope, is going to try to figure out, at least measure sort of the rate and see if the expansion rate has changed and what that means. So, I mean, we really don't understand what happened at the moment of the Big Bang. It's possible something like inflation happened, but at the moment that's actually conjectural. But it's a good first guess. You got to start somewhere, and then start figuring out where the data agrees and where it disagrees. And I mean, a stupid question? I mean, come on. You know about inflationary cosmology. Cheers. You know?
Hi.
Hi.
I am going to go back to the Orion constellation.
Yes.
And with those two that you had next to the one of them in the traditional way, or the way I'm used to seeing it, there's a very bright star, and I was really surprised why that one wasn't all bright red.
Yes. Let's go look at the stars in Orion, because it's my favorite constellation, and I think I can do this. So let me make sure. Yeah, I can go back. This one here. Yes.
Yeah, so that one on the upper shoulder, why is it not all flaring yellow on
Yeah. I mean, that's a bastard. That one. I mean.
The same one down in the lower right.
So I mean, if you've heard of the star Betelgeuse. Yeah, that's Betelgeuse, and Betelgeuse has given us all kinds of trouble. So Betelgeuse is a giant extended star. It's dying, and it's actually red colored, and you can see that. If you have a particularly color sensitive eye, you can see it as reddish in the sky. It's so big that it's about out to where the orbit of Jupiter is in our solar system, and the star is about to go supernova any damn minute. And boy, do we want that to happen, because it'll be a show. It's so far away, it's not dangerous, but it's right at the end of its life. And even more than that, it blows out big billows of gas and dust, like it's about to blow up, and we all get really excited, and then it calms down for another 10,000 years, and there you go. The colors, I mean, the colors may be a bit exaggerated in this image, but the Betelgeuse really is this big extended red-colored star. But you notice in the infrared, you don't get a whole lot from it.
I know that's what the ones that didn't look that, the two on the extended, on the lower right and the upper left.
Yep. And especially, I mean, here's the Orion Nebula invisible, and you can see what it's like in the infrared. The sky really does look that different. Some stars, if they have a lot of dust around them, will be very bright in the infrared. Basically, heat is reflecting off big dust clouds around the star. Some stars, like Rigel down here, Rigel is a very, very hot blue star, and it really does burn kind of blue. But Rigel doesn't show up at all in the infrared. I mean practically nothing. And that's because Rigel, is actually, the star itself is actually relatively small compared to the big, dusty things blowing off dying stars. And so, yeah, it really is that different, yeah. And that's, I mean, that shows you why you have the different types of telescopes. And the sort of difficult thing about infrared is infrared doesn't get through our atmosphere. Water vapor absorbs infrared. The greenhouse effect, carbon dioxide, absorbs heat light very well. And not only that, but our atmosphere is warm. So, heat from the stars doesn't make it very well through the atmosphere. So you need to go to space for that. But your observations are entirely correct. I mean, these hot blue stars down here that are so bright in visible light, you can't even see them. Yep. Yes, hi.
That's going okay? Yeah. Look, thanks. I really appreciate hearing about how the Earth is actually increasing with dust that we collect from outer space.
Yes.
So yeah, is it getting? So it's getting bigger, is it?
Yeah. So go ahead. Ask the question. Yeah.
The second question is: you talked about a supernova that was like 1,000 years ago. Yeah. Is there any evidence of the dust that came out of that on Earth, or was it too diffuse? Yeah. So
two really good questions. One thing that I would like to research, because I'd be very curious about this myself, is how much is the Earth's mass both increasing and decreasing over time? Because, for example, think about photosynthesis. I mean, if you think 100 tons a day is a lot, right? All the plant life on Earth is turning light into starches. It's turning something that has no mass, light, into an actual food source. And I don't know how much that increases the mass of the Earth every day. But then plants are also dying and giving off gases and decaying. Also, the sun has a wind of particles, and we're largely protected from it. The Earth has a very good magnetic field, but we actually lose we lose atmosphere every day to the sun's wind. So there are mechanisms in space that take mass away, and there are mechanisms that bring mass in, and then there are things happening here on Earth as well that add mass or subtract mass. And so I actually don't know what the mass balance is, how much we pick up versus lose every day. And I'd like to learn more about that. And your question about the supernova. So yeah, the Crab Nebula is so far away from us that there wouldn't have been time for that particular explosion to mix in with us. So I should look up exactly. So the Crab Nebula exploded about 1,000 years ago, and so it took light. It took light about 1,000 years. Sorry, I should look up how far away the Crab Nebula is. I don't know offhand. I think the Crab Nebula is on the order of about 1,000 light years away. So the light got to us, but all of that dust and that material is traveling much, much slower. I mean, even though we said that shock wave, that material is going out at 3 million kilometers an hour, that's still very, very slow compared to the speed of light. So that material hasn't had time to get to us yet. But it may someday, and as we go around the galaxy together, we'll begin to mix together. But so yeah, most of the stuff that's in your body would be from stars that exploded longer ago than that, and we've had a chance to move around the galaxy and pick up stuff. Yeah.
My brain is really hurting now, but.
Oh, I'm sorry. I mean, Did
you work on the James Webb?
I did. Yes.
Cool. And how do you send these signals thousands and thousands of kilometers away?
Well, yeah.
And control the text and what it's doing.
It's basically just radio signals, the same as anything else. I mean, if you think about having, a remote-controlled radio car or like a remote-controlled drone up in the sky, right? You have either a microwave or a radio signal that goes back and forth that allows you to control your drone if you're taking drone pictures. And I mean, honestly, it's the same principle. I mean, we have emitters on the telescope that pick up radio waves or microwaves for the most part. We're just beginning to use lasers, laser communication from Earth to our satellites. We've demonstrated that. It was just a technology demonstration, but we actually got a laser to kind of stay coherent, stay aimed all the way out to Mars. So I think in the future, it'll be more laser comm communication. But it's really no different. It's just radio signals, and then the telescope then basically emails us back the data via radio signals and microwave signals. And we actually have a whole fleet, well, not a fleet, but we have a whole armada sort of all around the world of dishes, of radio dishes that pick up this information coming from space. And one of the things that I loved at the Jet Propulsion Laboratory, so I worked at the Jet Propulsion Lab for about 13 years, and then about 14 years at NASA Goddard. And an artist did this wonderful installation when you go into the main lobby at JPL, and it's all these little tubes of LED lights that go up and down from the ceiling, but they're actually showing you real time. The artist linked it to the data, which spacecraft we're communicating with and sending commands to. Like it would say Voyager, you see like little lights go up. And then in a couple more minutes, you'd see the lights come back down because it meant we were receiving the data from Voyager. So when you go to JPL, in the mission control, they have maybe 20 different spacecraft. There are little kind of avatars on the screen, and they show you when we're uploading commands and when we're downloading the data. And it's all radio and microwave signals. So that limits the amount of information we can bring back. It's like a dial-up modem, right? It's like 0, 1, 0, 1. I mean, with laser communication, we'll be able to do it thousands of times faster. They're like the Cassini mission, my favorite mission that went out to Saturn for 13 years and observed Saturn. And the modem was so slow. I mean, we couldn't download all the data we took. We had to download only the highest priority data because we basically, I mean, so Cassini launched back in the 90s, and anything we send up in space is like 20-year-old technology because it has to work in space. I mean, we were basically sending an old cable modem up there.
So I know all the jobs it's supposed to do before it's sent away, and you just send the messages which one to do.
Yeah. So, I mean, we, in real time, so we send a radio signal all the way to Saturn. That's going to take us like half an hour. The spacecraft picks it up and does the observation we take it to. I mean, you can talk to them. I mean, just like you can talk to a drone. You know, you can tell it what to do and what to take a picture of. It's the same principle, just over a longer distance. Yeah. Sure. Yeah.
Oh, cheers. Oh, my voice isn't that great. But, you started by talking about the constraints on James Webb to do the weight and space. Are you?
I'll repeat the question. Yeah, sure. Go ahead.
Yeah, sorry, my voice isn't that.
Fine. Yeah.
Are you?
I can hear you. Don't worry about it.
Are you excited about SpaceX Starship to be able to just whatever we think about the immediate goal of Starship, to be able to piggyback on that, to have to be able to have bigger and heavier things to go to?
Right. So his question is about the SpaceX Starship rocket and whether we're looking forward to using that to build bigger payloads and send more into space. Well, the answer is absolutely. First, we need to stop it from blowing up. It hasn't had a successful test yet, but it will. I think it will. So I often get asked the question about whether NASA thinks it's in competition with with SpaceX, other companies. You've got Rocket Lab here. And the answer is honestly, it couldn't be farther from the truth. NASA is not really in the business of building rockets. And we haven't been from the beginning. All the way back from the Apollo program, we actually bought rockets from companies. Through most of my career, we bought them from Boeing. Those were the Delta series of rockets. And so we've been buying SpaceX Falcon and Dragon rockets for the last 10 years. And they are amazing to see launch and land. I've been to many SpaceX launches and landings. And when the first stage comes back, after 7 minutes, it launches, it goes all the way to orbit, it'll pop a satellite off, and then lands 7 minutes later. And this 10-story building basically comes falling out of the sky faster than the speed of sound. And just before it lands, the retro rockets fire, it slows down and puts itself down. In my case, I've seen successful landings. And then right when it lands, you hear the sonic booms, boom, boom, because it just cuts its speed of sound right before it lands. The thing that I think a lot of people aren't aware of is that NASA commissioned the development of the Falcon and Dragon capsules, and we paid Elon Musk $45 billion of taxpayer money to do it. So Elon Musk is a government contractor funded by public money. And this is honestly the source of, I mean, what's happening in the United States right now is, I was having a little bit of a panic attack about it. Our Supreme Court just ruled yesterday that they're not going to do anything to stop what's happening. And unless you bring a lawsuit. So basically you don't have rights unless you can bring a lawsuit. And that's why I was actually looking for real estate. I just retired and I don't have any children. I'm going to take care of my parents, but I travel about half the time, and I'm sort of thinking, where's the next place I'm going to live? I mean, the idea that these billionaires are doing this out of their own money and out of their own power is just, it's a false narrative. You know, we paid for the development of that rocket. It's a good rocket. We use it, we buy it. We're not in competition. He's not building James Webb Space Telescopes. He's not building climate satellites. You know, at NASA Goddard, we operate 110 missions, and there's always some ending and some beginning, but about 110. And the entire budget for all the climate science, all the best climate models, all the Mars rovers, all the trips to Jupiter, all the weather prediction, all the sun observing, all the solar weather, 110 missions, you know, the health of the oceans, you know, a landslide prediction. We do that for $6 billion a year. And 110 missions that give, you know, data that saves lives every day. And $6 billion, I think we actually showed that there was more spent by the military last year on air conditioning. So the idea that we're spending a lot of money on this as well is another false narrative. You know, a nation as rich as the United States has that amount of money to spend. And New Zealand as well has money to spend on fundamental research.
Well, Daniel. I think, on that note,
I have some words. So kia ora koutou, ko tēnei Pritchard tōku ingoa. So my name is Bennu Pritchard, and look, on behalf of the board of the International Science New Zealand International Science Festival, it is my duty to thank some very important people. But before I do that, you would be most welcome here. Keep an eye on that real estate situation. I can assure you, we're all watching the news as well, and but you are very welcome. So keep an eye on Trade Me. As I would say, we'd be stoked to have you. Yes. So as I said, on behalf of the board, the New Zealand International Science Festival is a charitable organisation, and it has a board, and I am part of that. With many other people I can see here in the room tonight. But in terms of thank yous, I think the most important one, and firstly, is to you, Michelle. Ka mihi nui ki a koe. So thank you, big thank yous to you. For tonight's presentation, it was fantastic, but to also for all the other events that I know that you've done and that you will do while you're here in New Zealand. I think it's really lifting the profile of science, technology, engineering and math in Aotearoa, New Zealand, and we're very grateful for it, so thank you. The mission of the New Zealand International Science Festival is to inspire and engage people, all ages, around science, and to demonstrate the importance of science in our everyday lives. So it is a pleasure to hear you speak with such passion on these subjects, and I think I'm on very safe ground when I say that I'm not the only one here tonight who has been inspired and engaged. So thank you.